So this is the sixth section, chapter 1, complex numbers in the core year 2 book, and we're going to be looking at finding the nth roots of a complex number. Now, just like normal numbers, where you can find the square root, the cube root, the fourth root of a number, we can do the same with complex numbers. So we can find the cube root of a complex number, the square root, the fourth root, the fifth root, and there's a method we can use, and it relies on De Moivre's theorem, and we'll also be looking at what these complex roots look like on a Argand diagram. You'll see they make a nice pretty pattern. Now there's some information up here. I'll just probably write it out again. So the first thing is, if we want to find the roots of a complex number, the first thing we need to do is to write the complex number in the form r cos theta plus I sine theta. The reason we can do that is because we can find the nth root of a complex number using De Moivre's theorem. So the nth root would be r and then to the power of n, and then taking the argument and dividing it by n. Okay, now if you did that, you would only find one root. So let's put down where this comes from. So basically this is where the power is 1 over n. So sine theta. So we're basically we're doing that, yeah. So we sort of divide by the divide the argument by n, and it becomes r to the power of 1 over n. So it's the same type of thing we're doing. So instead of n being the power, it's 1 over n. Yeah, if you did that, you'd only find one root. But what we need to appreciate is that actually, if I were to write a complex number if I was to do one on the Argand diagram, so there's my Argand diagram with my real axis here, my imaginary axis here. Let's keep it nice and simple. Let's say I had this complex number that goes to 1, and I write it in the r cos sine theta form. Well, I could, this has an argument of 0 and a modulus of 1, so I could write it as 1 cos 0 plus I sine 0. Yeah, so that's one way of writing it. Because we choose to have the argument between pi and negative pi, or just before negative pi, we don't really appreciate the fact that actually, okay, the same complex number, if I go around like that, a full turn, that actually I could write the same complex number as cos 2 pi plus I sine 2 pi. It's the same complex number. It's just like, you know, it's an unconventional way of writing it. Okay, I could go around again. And I could also write it as 1 cos 4 pi plus I sine 4 pi. And in fact, I could keep going up by 2 pi, keep adding multiples of 2 pi, and it would represent the same complex number. Now, why would we do this? Because even though these angles here are not in the correct range, you'll notice to find the roots we need to divide by n. When I divide by n, I may actually end up with arguments, angles which are in the correct range. So we need to consider all of these multiples of 2 pi in terms of angles, otherwise we're going to miss roots out. We'll only find one root when there are actually others. Yeah, so we keep adding multiples of 2 pi. You'll see it in a moment when we do some examples. Okay, so we need to solve this. The first thing that we need to do is we need to write the number in the form r cos theta plus I sine theta. In this case, r is 1 and theta is 0. So 1 can be written as 1 cos 0, not cos theta, plus I sine 0. Right, so down here, solving part A, basically want to solve z cubed equals 1 cos 0 plus I sine 0. We want to find z, which means we cube root both sides. Like that. Using De Morgan's theorem, we can do the root of the modulus and divide the argument, or times the argument by a third, which is the same as dividing it by 3. Okay, so it's all about solving that. Now this argument that we've got here of 0, remember that can be any value which is 2 pi more than that. So the argument could be 2 pi, 4 pi, 6 pi. Yep. We want to keep adding 2 pi to the original argument. And if we generalize that, we could say, right, you want to add 2k pi to the original argument, where k is like 0, 1, 2, yeah, so that we don't miss any roots, we get all of the roots. So now what I'm going to do is write it as z equals, and I'm going to change the argument so that I now have 2k pi plus the original argument plus I sine 2k pi plus the original argument. So I'm just adding multiples of 2 pi to the original argument, like this. So let's see what happens when we've got different values of k. So if k is 0, what argument do I get? So I'm basically not adding anything to 0, then dividing it by 3, so I get an argument of 0. When k is 1, that will give me 2 pi over 3, so a different argument. Now, if I hadn't have added these multiples of 2 pi here, I wouldn't have got this argument. I would have just got that one and think, right, that's the only root, but there are more. And notice how, even though this argument here may not be in the range, when you divide it by 3, it is in the range. So a little bit like cast diagrams in a way. When you're solving equations, you need to divide something by 3 afterwards, or 4. Okay, our next argument, this will be, k will be 2. That gives you 4 pi over 3. Now remember, our argument must be between pi and negative pi. So I need to take 2 pi away from this to work out what the argument is in the correct range. So it's equivalent to negative 2 pi over 3. Now if I go on to 3 and work this out, I'll get 2 times 3 times pi plus 0 over 3. I will get 6 pi over 3. That's just 2 pi. Take away 2 pi to make it in the range. That's 0. So what happens is I end up going back to where I started. So here I basically end up going back here, and if I were to carry on I would end up getting that again, and then that again, and then that again. So I stop. Yeah, I'm not going to find any more new arguments. So my solutions, let's go over here and put my solutions down. My solutions all have a modulus of 1, because that's just the cube root of 1. And I have 3 distinct arguments: 0, 2 pi over 3, and negative 2 pi over 3. Okay, so let's write our solutions. Let's call them Z1, Z2, Z3. So solution number 1 is going to be 1 cos 0 plus I sine 0. Z2 is 1 cos 2 pi over 3 plus I sine 2 pi over 3. Solution number 3, cos negative 2 pi over 3 plus I sine negative 2 pi over 3. Now what I'm going to do is write these in the form a plus bi over here. So the first one is just going to be 1. If I work these out and work out the cos and sine of 2 pi over 3, I'll end up with negative a half plus root 3 over 2i. And then for the last one, if I work out the cos and sine of negative 2 pi over 3, I end up with negative a half minus root 3 over 2i. Okay, now part B, I have to be careful with space here. I'll do part B over here. I need to represent these on an Argand diagram. So we will have one of them here, that will be Z1, Z2 is going to be over here, Z2, and the third one is going to be over here, Z3. So you can see it forms this nice symmetrical pattern where all of these gaps here are 2 pi over 3. Yeah, and that may lend itself nicely later on to solving some geometric patterns. And we'll probably find that the roots of complex numbers often form these geometric patterns. And notice that cube root, how many roots were there? 3. And that might be useful later on as well. So we found a cube root, 3 roots. Maybe, that might give us a clue to what's coming later on. Okay, part C, show that the roots of 1, and we've got the roots of 1 here, 1, negative half plus root 3 over 2i, and negative a half minus root 3 over 2i. Show that can be written as 1 plus omega squared, where 1 plus omega squared is 0. Now what's interesting, and you can use your calculator to check it, is that if we called this omega, if we square it, we get the other root. Or if we were to call this root omega, if we square that, we get the other root. So each one of the other roots, they're squares of each other, so we could use either one for omega. And let's see what happens. So I'm going to do 1 plus, let's call Z1 omega, like this. And then this squared actually is the other root anyway. So if I were to square -1/2 plus √3/2i, if I square that, I get the other root. So I'm not just writing it, I'm writing down what that root squared is, which happens to be the other root anyway. So -1/2 minus √3/2i. And if you add those together, you get 0, because you've got 1 -1/2 is, which is 0, plus √3/2 minus √3/2 is 0. Again, this might be an important fact later on. So 2 important things that might be useful later on. Number 1, cube root of a complex number, we ended up with 3 roots. The sum of the roots is 0, and probably a third important fact is that the roots form this nice geometric pattern here. Okay, so we're going to solve this. Z to the power 4 equals 2 plus 2 √3i. So first thing we need to do is to write 2 plus 2 √3i in the form r bracket cos theta plus I sine theta, which means finding r, the modulus of that complex number. So it's going to be square root 2 squared plus 2 √3 squared. And if we do that, we get a nice answer of 4 exactly. And we need to work out the argument of that complex number. And we'll do a Argand diagram so I get it in the right place. So it's 2 across, 2 √3 up. So that's my argument there. So I can get that by doing the tan inverse. Let's call it arctan this time, because we're dealing with radians and we have a particular range of values. And that's going to be the opposite to that angle, which is 2 √3 over 2. And if we use the tan inverse of that on our calculator, we'll get √3 over, or pi over 3. So now we're ready to write our complex number in the correct form, or the form to answer this question. So we have r is 4, and we have cos pi over 3 plus I sine pi over 3. Okay, we want to find z, which means finding the fourth root of the other side, which means finding the fourth root of 4, and it also means taking these arguments, pi over 3, and dividing by 4. In a minute we'll write down all the other arguments that it could be, all the plus 2 pi's. Okay, so now let's write it in a form where we can then deal with all the multiple arguments. So still got that bit. So the other arguments are going to be whatever these arguments are here, pi over 3, plus multiples of 2 pi, plus multiples of 2 pi. So that's going to be 2k pi plus the original argument over 4. Now I've just written the argument down, I'm not actually cos of the argument. So I actually might move on to the next line because I'm not going to have enough space to write it there. So let's put it down here. So z equals 4, full root of 4, and then cos 2k pi plus pi over 3 over 4 plus I sine 2k pi plus pi over 3 all divided by 4, and then I'm going to put in the values of k to give me my different arguments. So the first thing I'm going to write down, I can work out what r is. So r is the fourth root of 4, which is basically the square root of 4, which is 2 square rooted. So r is 2, so we've got that. Set that to one side. So now let's make r equal to, not r, k equal to 1, or k equal to 0. So we can get the first argument. So if k is 0, we'll get our first argument as 2 times 0 times pi plus pi over 3 all divided by 4. So that's basically pi over 3 divided by 4, which is pi over 12. So argument number 1. Number 2, let's make k equal to 1. So 2 times 1 times pi plus pi over 3 all divided by 4. So if I work that out, that's 2 pi plus a third pi. So that's 7 pi over 3 divided by 4, which will be 7 pi over 12. So these are both in the range, so that's fine. K equals 2. So I'm going to have 2 times 2 times pi plus pi over 3 over 4. So I'm going to get 4 pi plus pi over 3. So 4 pi is, let me calculate 4 and a third basically. So that's 13. Let me just do on the calculator. 4 plus a third. 13 over 3 divided by 4 would be 13 pi over 12. Now this isn't in the range. It's too big. It's bigger than 1. So let's subtract 2 pi. Hope I've got enough space. And see what we got left. And we're left with 7 pi. Let's do that again. 13 over 12. Take away 2 pi. Negative 11 pi over 12. So negative 11 pi over 12. And then for k equals 3. 2 times 3 times pi plus pi over 3, not pi over 13, pi over 3, all divided by 4. Okay, so that's going to be 6 pi plus a third, which is 19 pi over 3, which will be 19 pi over 12 when we divided it. Again, that's out of the range, so let's take off 2 pi. And that leaves us, let's try it again, 19 over 12, take away 2 pi. These is negative 5 pi over 12. So I'm just going to highlight, these are my arguments here, 1, 2, 3, 4, and here's my modulus, So I'm ready to write my answers down with a pen rather than a highlighter. So my answers. First root, root 2 cos pi over 12 plus I sine pi over 12. In the exponential form, that would be root 2 e I pi over 12 or 12 over pi over 12 I. Number 2, only difference is that the argument is now 7 pi over 12. So that would be root 2 e I to the 7 pi over 12. Third root, root 2 cos negative 11 pi over 12 plus I sine negative pi 11 pi over 12. So that'll be root 2 e and negative 11 pi over 12. And the last one, root 2 cos negative 5 over 12, isn't it? Negative 5 pi over 12 plus I sine negative 5 pi over 12 root 2 e negative I 5 pi over 12, and we have our 4 roots. Now you may have thought to yourself, when we got to this bit, why didn't we do k equals 4? Well, if we did do k equals 4, we would end up with the same root as the first one. We'd end up going around the loop again. Yeah, because we said, well, in general, if it's z to the power 4, there are going to be 4 roots. So the reason why we didn't do that is because with 4, k equals 4, we would have ended up back with that. I'll prove it to you. So if k was equal to 4, we would have 2 times 4 here, pi, plus pi over 3. So that would be 8 pi plus a third pi. So you had 25 pi over 3 at the top, divided by 4 would be 25 pi over 12. Yeah, so we'd have 25 pi over 12 if we did k equals 4. That's outside of the range. Let's take away 2 pi. I end up with pi over 12. So with k equals 4, I'd end up with this again. But we've got 1, 2, 3, 4 roots. I'm not going to get another one, so we can stop there. So I've given my answers in the cos sine form here. I've also done it in the exponential form. I could have done it in the form a plus ib, but the numbers aren't particularly nice, like root 6 plus root 2 over 2. It's not particularly nice, so I've just left it in that form. The question doesn't specify actually which form to leave it in. Now before I carry on, I just want to talk about what I've got written up here in this box, because there are some things that we can generalize when we have what we call the roots of unity. Now the roots of unity are basically the roots of 1, the complex roots of 1. When 1 is a complex number, the roots of that. And what we found out is that for whatever power of 1, there are that many roots. So if I had z to the power 7 equals 1, I would find that there are 7 roots. And these would be called the 7 roots of unity. And there's also something special about these roots. These roots sort of form a geometric pattern. So if I had 7 roots, 1, I'm not sure if this is going to work, 2, 3, 4, 5, 6, 7. I'd have something like that. Yeah, not drawn very well. But I'd basically, if I were to join those ends up, like this, I would have drawn a regular, is it heptagon? Yeah, 7 sides, a regular heptagon. And that's this bit of information down here about all of these roots forming this geometric shape, heptagon. That in this case, because there were 7 roots, if there were 5 roots, those complex numbers would form the vertices of a regular pentagon. And also the sum of those roots is 0. Yeah, the sum of all of those roots of unity are 0, and actually they're sort of powers of each other. Very interesting, lots going on there. Okay, so before we solve this, we just need to rearrange the equation into the right form. That means taking away 4 root 2 from both sides and taking away 4 root 2i from both sides, so it looks correct. Next step is to write it in the form r cos theta plus I sin theta. So that's going to mean finding the modulus r, which is going to be the square root of negative 4 root 2 squared plus negative 4 root 2 squared, and that gives you exactly 8. Then we want to find the modulus, or sorry, the argument. So always draw a diagram so we know exactly where this complex number is. It's down here. This is negative 4 root 2. This is negative 4 root 2. And the whole argument is this. Now without that diagram, you may not have realized that. So whatever we get for this angle, we want to add this angle, which is 90 degrees, which is pi over 2. So our argument, and we also need to remember the fact it's negative. Yeah, so whatever we get, we want to put a negative. So this bit in red, let's color code it. So the bit in red is the arctan of minus 4 root 2 over minus 4 root 2, which is tan inverse arctan of 1, which is 45 degrees, which is pi over 4. The bit in blue, that's pi over 2. So we need to add to that the pi over 4. And what we'll get is 3 pi over 4. But because of the direction, because of where this complex number is, it's negative 3 pi over 4. So negative 3 pi over 4. Now, if you didn't draw an Argand diagram, you may not get that right. Yeah, you maybe not realize it's negative. You may not realize you need to add pi over 2. Just doing the tan inverse or the arctan of the two complex numbers or the lengths doesn't always give you the answer. It all depends where the complex number is, and you're not going to know that unless you draw your Argand diagram. Right, so now let's write it in the form where we have r cos theta plus I sin theta. So r is 8, not square root, a bracket, cos negative 3 pi over 4 plus I sin negative 3 pi over 4. Okay, so we're going to do the cube root of both sides, which means cube rooting r, and it means dividing each of the moduli. We need to divide by 3. Yeah. and the same with the sine. Then we need to show appreciation for the fact that there are other roots where we're adding multiples of 2 pi. So we need to add multiples of 2 pi to the original argument, then divide by 3. Add multiples of 2 pi to the original argument, then divide by 3. Okay, so let's work r out. So r is going to be the cube root of 8, so r is 2, so we can set that aside. That's going to be in front of all of our answers at the end. And let's go for different values of k so we can work out what the different arguments are. So k equals 0. So when k is 0, we're going to get an argument of 2 times 0 times pi minus 3 pi over 4, all divided by 3. So that's going to give me negative 3 pi over 4 divided by 3, which is negative 3 pi over 12, which simplifies, it is in the range, but if you divide the top and the bottom by 3, you're going to get negative pi over 4. Okay, so that's argument number 1. Okay, let's go for k equals 1. So 2 times 1 times pi minus 3 pi over 4 divided by 3. Okay, let's grab the calculator. So 2 minus 3/4. I shouldn't really need a calculator for this. 5 over 4 divided by 3 is going to be 5 over 12. So 5 pi over 12. Can't simplify that. That's in the range. So that's argument number 2. Let's go for k equals 2. Let's just highlight the arguments. Actually, no, we'll do that at the end. K equals 2. So that's going to be 2 times pi minus 3 pi over 4, all divided by 3. So that's going to be 4 pi, 4 minus 3/4. So that divided by 3. So 13 pi over 12. This isn't in the range. So let's take off 2 pi. So take away 2 from that, and I get negative 11 over 12. Negative 11 pi over 12. Okay, so how many have I got so far? 1, 2, 3. Right, we'll stop there. We know there aren't going to be any others. So our arguments are here, negative pi over 4, here, and here. Okay, it doesn't say which form to write our answers in, so let's write them in the cosine form and in the exponential form. So solution number 1, so z is going to be 2 cos, let's go for the negative pi over 4, negative pi over 4 plus I sine negative pi over 4, and I'll write down the exponential form, which will be 2e negative I to the pi over 4. Root number 2, 2 cos, let's go for the 5 pi over 12, so 5 pi over 12 plus I sine 5 pi over 12. Exponential form 2e to the I 5 pi over 12. Third and final root 2 cos, so we're going for negative 11 pi over 12 plus I sine negative 11 pi over 12 exponential form 2e negative I 11 pi over 12, just enough space. So there we go. So let's just highlight where our answers are there here. Here we go, in both forms. And right, you should be able to do exercise 11, 1F on pages 24 to 25.